Hi everyone and welcome to the show. Today we have Koen Bertels as a guest who will be talking about PISC and NISQ that are two concepts in quantum computing. I'll let Koen introduce those concepts and give the details himself, and he was kind enough to prepare a presentation as well for today's discussion. Koen has more than 10 years of experience in the field of quantum computing and is currently a professor in quantum computer engineering as well. So without further ado, let's jump into the interview and listen to what Koen has to say.
Yeah. Okay. So thank you very much for inviting me and that we can exchange a bit the ideas. So I'm a computer engineer by formation, and I'm a professor like that also. I've been that in Delft University of Technology, and I moved quite recently to the University of Ghent. I've been working on quantum computing for almost 10, 11, 12 years. Very much in the first phase on the hardware part. So a microarchitecture controlling two or three a couple of qubits, quantum bits. That was in the context of a collaboration with Intel. Yeah, so this is just, let's say, the background that you can see. But then I do see that, and that's so everything what we do now, or what people do now currently in hardware, is called NISQ. Yeah, it's called noisy intermediate scale quantum, and that's a term that was defined by John Preskill, who is a physicist from the United States. And so he really says, like, look, there are too many qubit technology in competition. They all claim to be good. And as a computer engineer, so building computers, I say they're all bad. Yeah, and that doesn't mean there's no future. I think it's an extremely powerful kind of technology, but it will take us much longer to reach a good quality. And so in order to cover let's say the where we are right now and where we want to be at the industrial and societal level. Yeah, we introduced a new label, which is a label that I defined with my new team. It's called PISC, stands for Perfect Qubits. Yeah, the perfect qubits, intermediate scale quantum. So the P represents perfect qubit. Yeah, and I will try to explain that a little bit further on. So this is what I think internationally we should be going much more for. Yeah, that is, we still need the physics people, the physicists, mathematicians, and computer engineers. So that's what I did in the first 7, 8 years in Delft, working on, let's say, the few qubits that they were making, semiconducting, superconducting, because it was with Intel. And so we developed a lot of things that we could actually test how good those qubits are. But this is not really very challenging anymore for a computer engineer, but super challenging for physicists. Yeah, but so that's why I decided to move, let's say, more towards the application side. And I started a company, which is something normal for me to do. I like to do really 10, 15 years look ahead, but I still want to have a clear contact with reality. And that's why a startup forces me also to look at concrete problems. So that's why I have the gray
Before
box
we
with,
go into the
yes.
Before we go into the slide that you're presenting here, could you maybe elaborate a little bit just on a very high level of what that company is? So we have now this presentation that introduces the NISQ and PISC concepts, and you'll also intertwine to some extent the company later on. But just as a starting point, could we maybe describe the company activities as well and how they relate to, just this PISC concept? I think that would be helpful.
Okay, so QBee is based is based in Leuven in Belgium, and the goal of that company is that we start collaborating with industry, and so that we'll say, look, what are the core problems for you, for which we don't really we will not have sufficient compute power anymore. Because in classical hardware, so as a computer engineer, I know these things, of course. The CMOS transistors with which we make these computer chips, we're at 2 nanometers scale. So 1 nanometer is one meter divided by a billion. So if we go below the 1 nanometer, we enter already potentially, at least, the quantum mechanical phenomena that we have. And so what we want to be doing with QBee is look at companies and say, look, what kind of compute power do you think you will need in let's say, in 10, 15 years? Because we have to start working on the quantum algorithms that we can develop for the kind of problem that you're looking at, yeah, and that we can execute maybe on real hardware in the future. So that's why this figure is interesting, because we still need to simply have the quantum computing logic terms, the concept that we need for any kind of quantum problem or a real world problem for which we need to have a quantum algorithm. And then maybe hope, and I'm pretty convinced that the physicists worldwide will keep on working on improving the quality, such that maybe in 10, 15 years after 2030, yeah, maybe 2035, maybe 2040, maybe it's sooner, that's very difficult to say, that we can really, again, map those or execute those quantum algorithms that we've been developing, we start developing for companies, we map it onto physical hardware. And then it will reach the market also as an operational quantum computational tool. That is the goal of QBee, to start working in that direction. Yeah. Okay. So this is the way that I think we should worldwide start organizing a little bit of collaborations between universities, research centers, but also companies. Yeah, and that means also companies that can be in any kind of field. So for now. I just had, and that's really this week, the confirmation of a large European space company that will give QBee a contract for multiple years. I cannot mention budget because I still need to negotiate that with them, but they made a formal approval from the CEO of this large company in Rome. Yeah, that they want to have a contract with us on quantum computing. They already work on other quantum aspects, but the quantum computing was still missing, and that is a very good new piece of information for that makes me as an entrepreneur very happy, of course. And I stay professor, but I'm always as a second part. I'm this entrepreneur, so that's why I keep on working.
First of all, big
Yes.
congratulations on that. Apologies, I think there is some delay in the audio, but big congratulations on the new customer. Do you have a theory why you in particular were chosen out of, I'm sure, other candidates as well? Was it your particular focus on the PISC concept that they wanted to put a larger emphasis on that particular methodology that you're developing internally, or would you say the determining factor was something else?
Well, this particular company, I've already been working with them for like a year. We tried to submit also a European project. That cost us a lot of very intensive brainstorming and reasoning. What are their problems? What can we do? Where are we? Where are we? And so a lot of companies, they look at the quantum hardware with all of the challenges. Yeah. So we still need, there's still 5, 6 maybe qubit technologies in competition. Maybe that will be reduced to 1 or 2, maybe 3. But at the application level, very little things are happening. And so if ever you want to build a computer, you need to have, let's say, on a classical machine that we're using for this interaction, we have maybe 2,000-3,000 gates on chip that we use for that can be programmed in particular ways, so that we can maybe visualize a video or make a chemical calculation or things like that. So I think why did they? I think my academic background certainly plays, because they're also very much convinced that now in this stage you need a PhD kind of research by multiple people, and also the fact that I'm a bit of an entrepreneur. So I did already other companies that were sold to actually big. One was a US-based company that was on genetics. So I tried to stay focused on computer engineering, but of course, computer engineering means you apply it also on certain kind of applications. So I think those two aspects, being professor and entrepreneur, made the difference for them also to understand that what I'm saying really makes sense. And so that is maybe the main reason. I have to ask them again why they work with me. Or want to work with me even more. But I think those are the main reasons. Okay, so this is a bit the big picture, how I think we should be organizing it a little bit more. Just also know that I'm now part as QBee, I'm part of QUIC, QUIC, which is the Quantum Industry Consortium, which came out of the Quantum Flagship, which is this large European project in which 1 billion euros is being put on developing quantum chips, qubits, good qubits. And so it's good that already there is industry involvement in let's say, in deciding, okay, we really need to start looking at the quantum algorithm or the quantum end user applications, because that also takes a lot of time, because we need to get maybe many more quantum gates quantum gates is how you operate on these qubits. Yeah, I will not go into the details of these things. Yeah, that would become too technical. But it's we're again in the analog world. Yeah, to which we have to connect the digital kind of classical machine. Yeah, and so analog reasoning and analog programming is completely different than, let's say, the classical digital way of reasoning and programming. So that is so that's why we really need to take enough time to look at the end user applications. And this is an open invitation for all quantum startups that are interested in doing that. And we should have much more intensive collaboration. And that is also the goal of what I try to do.
Is your perception of the startups in the space that too many of them are focusing on a narrow domain of applications? The reason why I'm asking that question specifically is I noticed quite a few startups in the space of cryptography, because that's, I think, the obvious hazard with quantum computers that might get sufficient computational power to sort of break some of the algorithms that, cryptography algorithms that currently exist. Is your view that amongst the players in the space, do you think there's a good diversification, or do you feel like people are too focused on a few topics?
Well, it's good because I think I have somewhere maybe a slide, and maybe I will because there are around maybe 20-25 papers to which everybody's always referring. 20-25 papers, and that goes most on the quantum hardware part, but quantum physics, the mathematics, the reasoning, yeah, but on a very limited number of qubits, yeah, and so the estimates also of how many qubits we will need, that is unknown, yeah. So sometimes you hear you need maybe millions of qubits, sometimes you say maybe 500 is enough. Yeah, that is very difficult to know. So I think there's still a lot of research that we need to do. And if you look at many of those papers that you can find that if you Google it, let's say quantum papers, relevant quantum papers, you will not find a lot. I think I have one of those slides in which I give the URL, yeah, and also a screenshot of that particular website, yeah, which is public domain information, yeah. So there's too much being done on, let's say, very small scale problems, but they always repeat kind of the same kind of algorithms that everybody's already using. And we really need to start thinking in a completely new way about genetics, which is what my last student, and now is a good friend, did in Delft. Yeah? He graduated last year in July. And he works on one of the things is on genetics. So we have a quantum version of genome sequencing. Yeah, and genome sequencing, you say, yeah, well, who's interested in that? Well, the entire medical industry and the pharma industry is focusing completely on DNA. So the idea would be that you go to your medical doctor and you put your finger in a device, and now it takes about a day to do all of the genome sequencing of your particular academic genetic profile. Yeah, and it should be done maybe in a couple of minutes or maybe in half an hour or so. But then your medical doctor can base his analysis on your current academic profile. Sorry, I get the word wrong. Your genetic profile. Yeah, so we really need to open it up. It's a window opening to new kind of fields. That is the core problem.
Okay, understood.
Yeah. So this is I continue a little bit in the slides, but so what we need, and this is really at the European level. So yes, evidently we still need to work on the quantum hardware part. Yeah. So I'm not saying this is not needed. This is absolutely needed. We should not forget that for classical CMOS transistors, it took us 40 to 60 years before it was stable and sufficiently scalable. Yeah, and that is basically in the 1980s. Yeah, you're maybe very young, but I'm already pretty old. So I was a young guy in the 1980s when the PC, the personal computer from IBM, was launched. Yeah, so we still have a long way to go, and so we still need to look indeed, like I show here, on, let's say, the different fields: chemistry, biomedical, space, engineering. Happens to be the topics on which QBee is working. Yeah, but it should be done with companies, company 1 to N. Yeah, there may be active locally or internationally. We need to have universities, and so this is a true statement for all of those fields, such that we have an understanding and the development of, let's say, quantum computing logic at this level, And yes, at some point, maybe there will be 2 or 3 of those qubit technologies, they will survive. Yeah, and they will reach the market. Yeah, it's very difficult to predict now. Yeah, I will make some prediction maybe later, but this is like a guess. Yeah, so I don't have any substantial information. So the only thing I do know is that we can work very substantially on these kind of aspects too. So yeah, okay. Uh, the noise of the notion of NISQ is also highly debated these days. Yeah. This one person that you can find on the internet said, yeah, what is this NISQ all about, basically? Yeah, actually, I was also earlier this year in Australia visiting also 2 universities there. And so I gave 2 talks at each of those universities, and one was with Andrea Morello, Italian. Yeah, he lives already a long time in Australia, but he's a very good physicist, and he only works on 2-3 qubits, semi-conducting kind of qubits. Yeah, and he also said NISQ is dead. For him, NISQ is dead. Yeah, okay. These are big statements. I don't know what, but what I want to say with Andrea Morello's work, he makes 2-3 qubits, but in an extremely good way. They stay and keep the information that they contain for multiple minutes, up to 5 minutes. Yeah, and they do always correct the quantum gate operations. So, and this I think is the correct way to go. Yeah, it's not about having 500 or 600 kinds of qubits that you need. It just happens to be. They refer here also to a university in Melbourne. Yeah, that university was in Sydney. Yeah, and I think this is really the right approach. So I think this is really the way in which we have to be careful of where we stand. This simply shows it's a bit of an outdated almost, but this is how much I did on aspects, and I worked a lot on the hardware, which is how I started working on the collaboration with my physicist and with Intel. Yeah. And so I worked with several. I was in Delft. Now I'm in Ghent. Yeah, I worked with Intel a lot. Now I start working a bit more with IBM. Yeah, and so that is a bit the context of what I'm doing. Yeah,
Maybe one question on what you said before when it comes
yeah.
to the robustness of individual qubits. So if we're in the NISQ space still, I guess the question is how big the impact is, or well, how much you can circumvent poor quality of the qubits by means of scaling. So you have topological quantum error correcting codes, for example, that could be a way of addressing that. But is your view that, so you made the statement before that you think the right way to go is perhaps fewer qubits, but qubits of higher quality that maintain their state and information for a longer period of time before decoherence takes effect. What makes you say that? Is it, are you not convinced that scaling up with poor quality, let's say, is a viable approach?
That we have already shown. Yeah. A couple of months ago, a part of the team of QBee, yeah, they were working on the chemistry kind of things. They participated in a worldwide competition organized by Deloitte, Germany. Deloitte is a consulting company, but they're also very active in quantum, especially in Germany. And so there were like 35 teams from all over the world, from Singapore to the United States, all over Europe. And we had to work on the global warming kind of problem. And so we had to show what kind of results of our model could have a positive impact. And so that's what every team did. And so many of the teams were, let's say, data scientists or mathematicians. And there was only basically one team from, let's say, from a chemistry kind of point of view, and that's the one from QBee. And we won that competition. Yeah, and so but with a substantial way different from anybody else. And so it was also co-sponsored by IBM. So we run it on a simulator of IBM, and IBM luckily also understands that perfect qubits are very interesting. Yeah, so nobody can make large number of qubits yet. Yeah, in a good way, and so it also has a simulator on the Qiskit platform. One you can run, let's say, perfect qubits, and one you can run the superconducting qubits from IBM. And we run it in both ways, and our results were good always in the perfect qubit kind of way. Yeah, and you get kind of crazy, and this is not a problem for IBM, to be very clear. because it's the same for Intel, the same for Alibaba, or it's the same for Google or whatever company we would be using. Yeah, because you don't control very well the qubit behavior and the information that you store in those qubits. So this is a clear indication that our vision of the PISC, yeah, really makes sense right now. Let's say we still need to work on the quantum physical behavior, yeah, but we can reason in terms of the algorithms. Let's simply say make abstraction of all of those things. So that is where this idea comes from, yeah. So we work with perfect qubits here. We don't want to go, let's say, to 400 perfect qubits, because yeah, you can have, let's say, 70 perfect qubits in superposition, and then you already need more memory than supercomputers these days can offer. So you really have to shrink down your problem, but you have to focus on the logical states. How many steps, quantum steps, do you need to make before you reach a good result in your quantum algorithm? So that is the main reason of our PISC approach. Okay, so everybody may know, maybe everybody knows Intel, because everybody's been using Intel chips and processors for decades. And one of the founders of Intel was Mr. Moore, and so he discovered along the decades that he worked, and he died unfortunately like 1 or 2 months ago. Yeah, but he discovered also that the number of transistors that we had doubled almost every 19 months, so close to 2 years. And so that is Moore's law. That is called Moore's law. So this trend still keeps on going, but of course the number of transistors that will be made will stabilize. Yeah, so we cannot make more because we have to shrink them to smaller and smaller. If it's smaller than 1 nanometer, we don't know if they will still be useful. Yeah, so we're now at 2 nanometer, and I think this will be the borderline. Yeah, and then we have to make a change maybe to this qubit technology again. Maybe a new Moore's law will pop up again. Yeah, that is very difficult to say. Yeah, but maybe a second Moore's law will pop up. Yeah, by doubling the number of qubits that we will have, but the quality needs to be substantially improved. Yeah, and you see also in the black graph here that the compute power is kind of stabilizing. It's stopping. It's not growing anymore. Yeah, and it's only in let's say the mid 2000, around 2005, that Intel started adding co-processors to the chip, and then you do see an increase again, but now it's stabilizing again. So that is where we are in classical hardware. Yeah. What is it in the quantum hardware? Where are we now? This is the overview. Yeah, and the last Nobel Prize for Physics went to to 3 people, and one of them was an Austrian person working on neutral atoms. So it's not really in this figure, yeah, but you have semiconducting, ion traps, photonics, superconducting, and still some other kinds of technologies. And so the largest companies
And what does this one
worldwide.
represent?
Yes.
Is it the amount of effort put into each category in terms of research grants, or what are we looking at in this pie chart?
How big the companies are that are working on these things, how big their budgets are.
Okay.
So this is mostly Intel. Yeah, this is IBM, Google working on superconducting qubits. Alibaba is Chinese, working on superconducting. In China, also photonics, and the United States, and actually in Northern Europe, in Scandinavia, photonics is still very popular. Yeah, so this simply means how big the budgets are that are being put on, let's say, those kinds of qubit technologies. Yeah. And so
Okay.
I mentioned here specifically the Scandinavia suggestion. They say, look, for now, for the next 5 years, everybody can still work on whatever they want to do. But in 5 years, we want to make a choice and say we're going to select maybe 2 qubit technologies and then see how good we can make them and start making a quantum accelerator out of these things. So that is the plan for Scandinavia, and I think it is a correct way. It's not what Europe is doing. It's not what the United States is doing. Yeah, but I think the Scandinavian suggestion really makes sense. Yeah, especially if you can combine it with people like Andrea Morello from Sydney, yeah, University of Sydney, New South Wales. Yeah, that is very very promising, I think. So yeah, I already mentioned NISQ and PISC. Yeah, why is it needed? because when we look at, let's say, the CMOS transistors, we have errors there too. Yeah, 10 to the minus 15 minus 16. So 10 to the minus 9 is 1 billion. You multiply it by a million or by 10 million, you reach minus 50 minus 16. So that means we can handle those things. Operating systems, chips, etc. We handle those things. In the quantum world, we have errors, yeah, meaning destroying the qubit and the data that we're storing in those qubits every 100 or 1,000 operations. So the error rate is so incredibly high, and I've not met many physicists, yeah, and computer engineers neither. Eh? So I'm as well guilty about these things, but I don't have enough physics background. But I would like to see that people start moving, let's say, -4, -5, -6, -7, yeah, because then we really see a way forward in stabilizing the quantum technology. So we're not there yet, yeah. So we have to avoid, of course, that there's this hype cycle. I do hope that the people that will be listening, they do know Gartner, which is a consulting company like Deloitte, Gartner company in the United States, and they've been looking at so many different technologies, and they discovered for each of those there's always a hype cycle. So the hype cycle is really what you see here. Everybody's super enthusiastic in this phase. They say, oh, it's amazing, incredible. We get the greatest innovation ever, and then there's a top, yeah, because none of those things deliver what is being promised. Then there's a lot of disillusion, basically. And it's only much further down that maybe companies and in universities will pick up the technology themselves. I added myself in this figure that I took from Gartner. The dotted line here and the red line here is quantum computing. I've not found the graph of the hype cycle, let's say from 2019 on, where quantum reappears again. So maybe I cannot interpret why they did that, yeah, but I do believe that in quantum also we're maybe reaching the summit of this hype, yeah, and I want to avoid that universities and companies stop investing in quantum computing, because I've never seen, as a scientist, any that much promising technology at the computer level.
Is your view that the hype cycle is close to its peak now? So I'm just noticing on the graph, this one is from 2018, and the estimate by Gartner is that quantum computing would reach the plateau of productivity in this graph in 2 to 5 years at that point. So according to them, sort of an upper estimate for the time it would take to reach the plateau would be 2023. Is your view, like, where would you say currently, if you had to place quantum computing in this graph, where would you place it right now? Would you say it's close to the peak of the graph, or have we come further than that?
No, I think we're close to the gap, to the top of the hype. Yeah, there are also physicists that start warning for that. They say, look, yeah, don't forget there's a hype cycle, right? Because if we suddenly withdraw all of the money and all of the investments in quantum computing, we lose also a lot of information and knowledge in people, and also people that are still motivated by that. So I think we're very close to the top. Yeah, and maybe that is the reason why Gartner stopped. Maybe there's a new one. Yeah, but I made this slide a couple of months ago, and I could not find a later one so I do believe that we're very close to the top. Yeah, this does not mean there's no future. I do believe, but it will still need to figure out what qubit technology will win, will be much better. Yeah, and so if you look at how many companies in China and in the United States are working, then superconducting seems to be quite promising, but I can be completely wrong. Yeah, and photonics may also survive, because that's mostly for communication purposes. Yeah, and so, but again, this is it's a black space now. You look inside the black box and you don't really know how the others position themselves towards each other. So, but I think we're very close to the top of this hype cycle. Yeah.
Okay.
So yeah, that gives a quick overview of how I worked on this full stack. Yeah, which now worldwide everybody's using. Yeah, I started working that was the first thing I did with my students and a young colleague from Spain. Yeah, we started defining what these layers are, and this is the latest evolution. Yeah, I will not go into. I will come back in this slide. Yeah. So
So just on a high level, this is the quantum accelerator that you're developing at the company at QBee.
well, yeah, but the quantum accelerator is still a virtual machine. Yeah, because we do the simulations with perfect qubits on a perfect qubit simulator. And so that means we
Yeah.
reduce the number of qubits, but we can go very far in the quantum gates. So there is indeed already one quantum algorithm that we developed, that my good friend Aritra developed, yeah, and that is on genome sequencing, yeah, the quantum way, yeah, but we have to reduce it to the number of short reads, yeah. It's too long to explain that, yeah, but an American company, Illumina, that delivers their machines worldwide to all hospitals, universities, research centers that do DNA analysis. And so they bought actually my second company that I made. Yeah, that's boasting maybe, yeah, but we wrote the software in a very efficient way. So, but we simulate it on our simulator. Yeah, so that's why we still look at this genome sequencing, because that is an operational version. I can demonstrate that wherever I am in the world, that connects to the computer here in the office in Leuven, yeah, and executes the algorithm and sends back over the internet, yeah, the results. So this is something we can do, but very small scale. We're not yet we have not yet the experience with good physical qubits. Yes, we do have access to physical qubits, but they're not good. Yeah, so the perfect qubit algorithms are still outperforming the physical qubit algorithms. So that is true. Yeah, but this is again why we need many more collaboration in the green box in the graph I showed earlier, between universities, research centers, and companies. Yeah, and we still need, of course, collaboration in universities and quantum hardware providers. Yeah, that is also true. Yeah. So this was what I mentioned earlier. So you see here, it's a Wikipedia kind of thing. Yeah, these are like 25 papers that people always keep on referring to, and they're very important. They're very challenging. Yeah, that is absolutely true. Yeah, but we really needs to widen it up to more fields, such as also computer architects and that need to build a quantum computer at some point. They get more and more, let's say, quantum gates that they need to implement. We also need some kind of quantum software. Yeah, and again, we are not there at all. Yeah, yeah. So this is really an open invitation for many people or universities or companies to start looking at those aspects. So yeah, this is what I already mentioned. So the number of qubits for now is not so important because you can never go very far. Yeah, but it's a quantum computing logic which is important. Yeah, and that is where we need to put more emphasis. Let's say as a collaboration. I mentioned Deloitte earlier. Yeah, and here you see two of my students. You see here the Delphine. She's Belgian. Yeah, and Kurosh is Iranian, and so they contributed to this competition and they won this they won it. Yeah, you see many other competitors here. Yeah, but the big participation was much bigger, but those were only 5 teams were invited, of which QBee was one. Yeah, and we won that entire competition. So this is very nice to see that it makes sense that this particular kind of PISC approach now already can work on concrete problems in a quantum way. And then if ever we get really good quantum chips, and that will happen too, but it takes much more time. Yeah, then we can immediately start integrating and scaling it up to larger problems, and do this implicit parallelization, because this is an important aspect that I don't want to talk about right now because it may lead us to too long. Yeah, but the fact that we have multiple layers of qubit states, yeah, that basically means it's an implicit way of applying the same kind of quantum gate. You do that on all of those layers in parallel in an implicit way. You don't need to program anything. You first this layer, then that layer. No, it automatically goes in that layer. And this is what I call implicit parallelization versus the explicit parallelization that we still need to do if we have multiple processors. Yeah, you need to explicitly define this data goes to that processor, etc., etc. So the potential of quantum is still incredibly good. Yeah, but we need much more time, and also universities need to rethink a little bit some of their education and things like that. But Yeah, so you understand that this is a very challenging kind of field, but it is amazing. So
Would you
so
say in the development of the algorithms that people
yeah.
are taking the noise into account as well? Like not just in the proclaimed approaches that they're taking to quantum computer development, but also let's say in universities when there is an emphasis on algorithmic development for quantum computers. Are they using the PISC approach, just that they're not referencing it in the proper way according to you, or is it that they're actually trying to take the noise into account in trying to develop the algorithms in the first place?
No, that's a good question, Nicholas. But because I do think that many people already do much more PISC relevant kind of research, yeah. But nobody knows this word PISC, yeah. So everyone will call it NISQ, but yeah, sometimes they do NISQ. I say you cannot call that NISQ, yeah, because well, for various reasons. So many people do PISC, yeah, because they have to reduce everything to, let's say, a small number of qubits, because you can never go to large number of qubits. Yeah, physical qubits for sure not, but even let's say the perfect ones, yeah, that IBM is offering and other platforms they also offer it now. Yeah, it always stays very small scale. Yeah, so but
Mhm.
this is a good starting point. But we should orient ourselves and say call this PISC, and then we know it is perfect qubit, and we call it NISQ when you really look at the physical implementation. Yeah.
Okay.
So yeah, that's basically the so the advantages I already mentioned that. So we need especially in point 4 here, we need a larger number of quantum gates than what we have right now. So the 25 gates that we have right now, that is a bit, yeah, I will not say ridiculous, but it is too small number to look at the wide variety of topics that we need to look at, let's say from an algorithm point of view. So that is clearly not possible. Therefore, I'm repeating myself. We need this international collaboration, industry, universities, internationally, at the European level, yeah, worldwide, yeah. But okay, we're now in Europe, so in the European context. So that is why we need those kinds of things much more, such that we can have, let's say, a full stack implementation, yeah, and that we can actually at some point, yeah, and that may take 10 years, maybe 5 years, but I would be very surprised if it only takes 5 years, but maybe 10, 15 years, that we can go and have all of these algorithms mapped on, let's say, a quantum physical chip, yeah. And so that is, I think, the main challenge that we as humanity still have to try to solve, so that we can really build maybe bigger models, yeah, to look at the global warming, the pollution, the poverty, yeah, and we have also industrial kind of problems for which we need those kind of compute systems. So that I think is yeah. So that does not mean that we don't need to work on the microarchitecture. So this is something I built when I was doing work for together with Intel. Yeah. Again, I will not explain those things, but of course, I did change the chip name, the quantum chip name. It's superconducting photonics, whatever it may be. Yeah, but you do need some digital kind of a control of these things. Yeah, again, I will not explain those things because now we modified it for our simulator that we have on the machine that we're using here. So much smaller memory. Yeah, doesn't have all of the features. We do simulate. We do store some information on the amplitudes. Yeah, which are these parameters on which we're actually working, applying all these quantum gates, and we manipulate the values of these amplitudes. They can translate that into probabilities, as we say here. But that again, that would lead us too far to explain that here. But this is our current microarchitecture that controls how we execute, let's say, on our simulator, the quantum algorithms. Yeah, this is simply a show the summary of what I already referenced. So the genome sequencing, yeah, what Ritra, who is also QBee co-founder, and is doing a postdoc now in Delft, yeah, he's been working on, and he developed. So from here on, it really becomes quantum computing logic, yeah, and I think this is very important to understand. Yeah, this is just an example of the quantum gates that he discovered that should be very useful, let's say, to implement in the hardware, but you still have to transfer it. The compiler, yeah, translates that into the current available set of gates that we have in physical simulations systems.
Mhm.
So
Do you want to
yeah,
describe the actual genome sequencing problem that was solved, or the high-level approach for how you tackle that problem?
well, well, the DNA for any living
Exactly.
entity on this planet only has these four amino acids. Four, yeah, too complicated to pronounce, but the CATG, yeah, that's the first letter always.
Mhm.
Yeah, the human genome has 1.5 of those GSCs, GSCTs or whatever. Yeah, and so you need this Illumina reader. So if you take, let's say, blood or a piece of skin or hair of anybody, it always has those 1.5 billion CATGs, and so you need to model that. Yeah, so these are, you get short reads from these Illumina machines, because no Illumina machine, and there's nothing else on the market right now. China is also very active on these things, but I don't know their machines. But Illumina is also used in Europe, yeah, and they make short reads of those 1.5 billion. So the genome sequencing is to make these short reads to map it into the reference genome of the human or whatever entity that you're studying. Yeah,
Mhm.
um,
And how
so
is
that
that
is
mapping made so much more efficient by means of quantum computers?
because if you look at this thing, you can I already mentioned implicit parallelization. So I have multiple. These are the short reads, for instance, short reads, and then you see yellow, two yellow things. There's a good match with, let's say, the reference genome that you're looking at. Well, the reference genome is initially is here. Yeah, you can parallelize that, quantumize that also a little bit. Yeah, so then this becomes, let's say, the four different base states that you can have in your quantum bits, in the qubits, and then you can start mapping it. This is the short read, so you need to see where does this short read map on the reference genome. Very small scale, absolutely, but it's more about the proof of concept of the quantum logic. And so you see here, we have two yellow ones. That means we have a good map. We have a perfect map. And here it's gray. Yeah. So here we only have a partial map. Yeah. And the same here, we have no map. Yeah. And also a partial map here. So you can then say, okay, it's apparently this one with the best uh, mapping distance or Hamming distance. That is all technicalities. Yeah. So here we see this is a perfect match. So this particular short read should be mapped on this location 00. Yeah, and this is then the output that you give to the human, to the entity doing this mapping. So this part,
Mhm.
yeah, this is all done in an implicit parallel way. So in a classical way, you would say, I'm going to first do this, and then I'll look that, and then I'll look on this one, and then I'll look at that one. In quantum, this is not happening at all. It immediately goes on all of those things in parallel. So if I'm talking about really 1.5 billion, yeah, I'm 1.5 billion, yeah, CATGs, yeah, the massive parallelism is incredible. We cannot yet build it, very clearly. We cannot yet build it, so we have to wait for that. Yeah, so that is the biggest advantage that we can hope to get from quantum computing, but it will take much longer than what in the media you read or what even some companies may claim. Yeah, it will take much longer. Yeah, and it's an open invitation for universities, but also for companies in whatever field to start reasoning about this quantum algorithm kind of concepts that we still need to develop and test. That is basically the core idea of our approach. Voilà, that's basically the storyline of what I was wanting to explain about the PISC approach. So perfect qubits, small number of qubits, but much longer set of gates and steps in the quantum circuit, so that we can verify with classical algorithms. We can verify how good the quantum algorithm is, and this is where we won this Deloitte competition. This is where we show that the genome genomics we tested, of course. The other company that was sold to Illumina is BlueBee. Yeah, I like the name being a company name apparently. Yeah, but BlueBee implemented the software in a very efficient way, so we could verify our genome sequencing quantum-wise against the classical algorithms from BlueBee. So in that way, and that is an open invitation again for multiple companies and scientists to do those kinds of algorithm checks. Voilà. That is in
Mhm.
that is in short the global message that I want to bring with this kind of concepts that we're introducing.
Okay, I think that's very good. We're also rolling up on time, so we should probably conclude the discussion. But just in terms of your engagements now, going forward as well, what are you hoping from maybe, let's pick the academical perspective perhaps, going forward? So you alluded to it a little bit before, that there are some changes you would like to see in academia. Are there any particular things that you think are lacking in the way people are educated regarding quantum systems that you would like to change?
Well, there are basically two things. One is in education. Yeah, I think university should start introducing quantum computing logic parts in any course, in any field. So it can be in chemistry, can be in finance, can be in biomedical, can be in engineering. Yeah, that students already get a feeling with what are these concepts, because it is a completely orthogonal way of reasoning, programming, yeah, and doing the mathematics. So the mathematics is very specific. Yeah, so you really need to educate people, preferably at master level, and then let them do a PhD, supervised maybe also by colleagues, professor colleagues that are motivated to go into that kind of field. Yeah, and it's not easy at all. Yeah, so it's for education and research. This is, I think, where universities should take more initiatives, yeah, to embed the quantum computing logic into their university operations.
When you say quantum computing logic, how in depth are you referring to then? So, if that would be sort of in a wider scope of educations, like a lot of different programs would have this line of education, what do you think should be the focus? Because I guess if you wanted to establish the mathematical fundamentals, that would take really a long time. I mean, studying physics previously, it took us, we studied mathematics for years before we even started with the quantum physics. Are you suggesting to proceduralize, sorry for messing up that word, the way in which people interact with quantum computers to make them more familiar with the conceptual fundamentals of it, or what's the idea?
Well, luckily, the mathematics that you need is very close to the mathematics, the matrix algebra that we already know. However, specifically for the quantum gates, for the quantum operations, and also the qubit, how they interact with each other, this tensor mathematics that we need to apply. Yeah, and this is a very specific way of combining matrices. Yeah, it is a very specific way of combining, doing a matrix multiplication, yeah, which is done, that we do need, because like this tensor mathematics was developed maybe 70, 80 years before even quantum mechanics was defined. Yeah, so it's not because of the quantum that they invented this mathematics. It simply turns out that it's a very smooth way, yeah, intuitively quite good way of formulating your quantum gates and your qubit states into that particular mathematics. So maybe the mathematics should be extended also with these tensor concepts. Yeah, but also the examples that we give is, let's say, if you take let's say chemistry. Yeah, that's what we see now in QBee also. Yeah, so one of my colleagues and a lady, she has PhD in chemistry. Yeah, she worked for decades already in industry and also on nuclear aspects for chemistry. And so now she's almost like a year working on the quantum aspects of chemistry. And it's may sound like a joke, but it shows how difficult it is. She said, I thought I understood everything in chemistry, but now when I'm looking at these quantum computing concept things, suddenly nothing is clear anymore for me. I said, look, Tamara, I warned you in advance. This is most likely the most difficult thing. So it does not need, let's say, too many. It doesn't need new students and new researchers, but it's simply focusing on your field and try to translate that into quantum computing concepts. And this, I think, is very important and should not be underestimated in understanding how important it is that we also start doing that kind of work and research right now.
Perfect. I think that's a great summary for your views of the industry. So, with that, people that want to get in touch with you, is there a particular place that they should reach out if they're looking for collaborations or just insights on various quantum computer topics?
Well, I think it's important that you as universities, I don't know, well, university is very difficult. Universities are pretty static, I have to say. Yeah, that's my personal experience. Not Delft was a very, very ambitious university. But when you look a little bit at the Belgian university, kind of, okay, yeah, oh, we'll see, yeah. But companies, I think they're a bit more elastic, and they really look 10, 15 years ahead. So if companies are interested, they should try to become part of, let's say, this QIUC, the quantum network. They also a very good German network. It's called the Quantum Business Network, and there may be others, yeah. But I think those are very important to be part of those networks. It's close interaction, close collaboration. You get also some scientists. Yeah, I have a bit of a double role there. Yeah, but you do get to meet other people that are reasoning in a joint way about these quantum computing challenges, and I think that is really very important. So, and of course, you can look at my website, and maybe you will send around my QB email. It's Koen Bertels at qb.eu. There you can always ask me questions. I'm on LinkedIn, etc., etc. So I will try to inform you and direct you to where you can find relevant information.
Then the only thing I'd left to say is thanks a lot for taking the time to present. I enjoyed the presentation very much, and yeah, I wish you a great rest of your week.
Okay, thank you very much. Thank you. See you next time. Thank you.